Welcome to This Explainer. Today, we're taking a seriously fascinating journey into the world of transistor audio power amplifiers. If you've ever stopped to wonder about the absolute engineering magic that takes a barely detectable electrical signal and turns it into booming, room-shaking sound, well, you're exactly in the right place. Let's get right into it. So, think about this core question for a second. How does a tiny whisper into a microphone manage to power a massive stadium speaker? I mean, a microphone generates a signal so incredibly weak, we're talking just a few millivolts. But a giant loudspeaker? That needs raw, physical acoustic power to actually move the heavy air around it. Bridging that massive gap between a microvolt whisper and real physical muscle, that's the exact puzzle we're solving today. Okay, here's our quick roadmap. We'll start with voltage versus power amplifiers, then talk about heat, efficiency, and distortion. From there, we'll dive into Class A power amplifiers, move on to Class B and push-pull setups, and finally look at the actual stages of practical amplifiers. Let's start with Section 1, voltage versus power amplifiers, and understand the basics. You see, the first few stages of any multi-stage amplifier deal with small signals. Their only real job is pure voltage amplification. They take that tiny input from a cassette, CD, or antenna and just make the voltage bigger. But here's the thing. Voltage alone doesn't have the actual current required to move a heavy physical speaker cone. It just doesn't. That is exactly where large signal or power amplifiers come into play. This final stage focuses its entire effort on handling high currents to drive low-resistance, heavy loads. It is literally the heavy lifter of the circuit. Just look at this stark contrast in these engineering parameters. A voltage amplifier relies on a really high beta, greater than 100, but it runs on a tiny collector current of about 1 milliamp. The power amplifier, totally different story. It actually sacrifices beta, dropping it all the way down to between 5 and 20, but in exchange, it pushes massive collector currents, well over 100 milliamps. And notice the coupling. Power amplifiers almost invariably use transformer coupling. Why? To achieve a very low output impedance, something like 200 ohms, which allows for maximum power transfer right to the speaker. Moving on to Section 2, heat, efficiency, and distortion. Or really, how we combat the absolute enemy of electronics. Because when you're dealing with these large signals, you run headfirst into a massive problem: thermal runaway. Since a power transistor handles such huge currents, almost all the heat is produced right there at the collector base junction. And it creates this incredibly dangerous cycle. As the transistor operates, the junction heats up. That heat generates more electron hole pairs, which spikes the collector current. And what does higher current do? It produces even more heat. If you don't actively stop it, this unstable spiral just keeps going until the transistor is completely cooked, permanently destroyed. So getting that heat out of there is absolutely crucial. And the practical engineering solution is beautifully simple. The heat sink. We've all seen them. By mounting the transistor directly onto a piece of metal, usually aluminum, we massively increase the surface area. This gives all that dangerous heat trapped at the collector junction an escape route safely into the surrounding air. It keeps the temperature in check and completely shuts down thermal runaway before it starts. All right, Section 3, Class A power amplifiers and continuous current flow. Now that we know the stakes of handling heavy power, let's look at how engineers actually classified these amplifiers. Take a look at the AC load line. In a Class A power amplifier, the operating point is set up so that collector current flows continuously, 100% of the time, throughout the entire full cycle of the applied signal. Now, the huge upside here is that the output wave perfectly mirrors the input wave, giving you the absolute minimum distortion, but there's a pretty massive catch to running current nonstop. And that catch is efficiency. For a basic series-fed Class A amplifier, the maximum collector efficiency is a shockingly low 25%. Yeah, 25%. That means 75% of the precious DC power you're pumping into the circuit isn't even becoming audio. It's just being burned off as completely wasted heat. Now we can try to improve this, sure. By using a transformer-coupled Class A setup, you can mathematically push the theoretical max efficiency up to 50%. But honestly, in real-world practical applications, once you account for power losses in the output transformer and all the other components, your actual efficiency hovers around a really wasteful 35%. If you're building a battery-operated or high-power system, throwing away that much energy as heat, it's just not going to cut it. Which brings us to Section 4. Class B and push-pull configurations, time to maximize that efficiency. To solve that glaring inefficiency problem, let's do a side-by-side comparison. Over on the left, here's our old friend Class A, just running constantly. But on the right, we have Class B. Now, in Class B, the transistor is biased so that zero signal equals zero collector current. Current only flows during the positive half cycle of the input signal. When the negative half hits, the input circuit is reverse biased, and the current completely stops. It is basically resting half the time, which saves a massive amount of power. But wait, cutting off half the signal creates an obvious problem: really severe distortion. You are literally throwing away half of your audio wave. Because of this, you will never, ever see a single Class B transistor used all by itself for audio amplification. The output wouldn't sound anything like the original track. So how do we get the incredible power-saving efficiency of Class B without the awful distortion? Simple: teamwork. Enter the push-pull amplifier circuit. This clever design uses two transistors placed back-to-back, with both of them operating in Class B. Think of it like two workers seamlessly passing a heavy load back and forth. Each one gets to take a well-deserved break while the other one works. Let's walk through how this perfectly rebuilds the wave. The center-tapped driver transformer feeds equal and opposite voltages to the two bases. So transistor 1 handles the positive half cycle of the signal, while transistor 2 is completely cut off. Then they tag out. Transistor 2 amplifies the negative half cycle, while transistor 1 gets to rest. Finally, the center-tapped output transformer grabs these two separate halves and seamlessly stitches them back together into a pristine, full continuous sine wave, feeding it right to the speaker. And the result of this brilliant tag team approach? The push-pull Class B setup hits an incredible efficiency of roughly 75%. We just jumped from the totally wasteful 25% of basic Class A up to a highly efficient system that runs cool and still delivers perfect audio. And that is exactly why it's the industry standard for power stages today. Finally, Section 5, Stages of Practical Amplifiers. Let's put the whole picture together. To get from that tiny whisper all the way to stadium-level sound, the signal essentially travels through three main stages. First, the voltage amplification stage takes those incredibly low voltage signals, we're talking less than 10 millivolts, and bumps them up using one or more voltage amplifiers. Second, the signal hits the driver stage. This is usually a Class A power amplifier with a step-down transformer, and it provides the essential intermediate power to actually drive the final transistors. And third, we reach the output power stage, which utilizes that highly efficient push-pull Class B setup we just explored to directly feed the loudspeaker. When you look at it mapped out, you can really see how beautifully orchestrated this entire process is. You just trace the signal. It starts out super weak, gets a major voltage boost, moves into the driver stage to prep the power, and finally slams into that massive power stage to operate the output device. It's just a seamless chain of specialized engineering. To sum up our entire journey, this quote from the source material absolutely hits the nail on the head. A practical amplifier always consists of a number of stages that amplify a weak signal until sufficient power is available to operate a loudspeaker. The real magic here isn't found in one single miraculous supercomponent. It's all in the intelligent staging and the careful handoff of the signal, from a tiny voltage amplification all the way to that high current power delivery. Which leaves us with a pretty compelling final thought. We've seen how ingenious designs like the Class B push-pull completely revolutionize things by bringing efficiency up to 75% and solving the terrible heat waste of Class A. But, as we constantly demand smaller, cooler, and immensely more powerful audio devices in our daily lives, what future engineering leaps are we going to need to push that efficiency even closer to 100%? It's a massive challenge, and one that audio engineers are literally still tackling today. Thank you so much for joining me on this explainer. I hope this helped shed some light on the incredible, invisible forces driving the sound all around you.